cockpit switch left in the wrong position blinded a test pilot to a 15-degree drift in his own flight path, and by the time he noticed, his aircraft was already sideways at Mach 5, 60 miles above the Mojave Desert. On November 15, 1967, Air Force Major Michael J. Adams became the only pilot to die during the entire 10-year run of the North American X-15 program, a rocket plane that had flown 199 missions without killing anyone. He was on his 7th flight in the vehicle. He had just become, in the final seconds of his life, one of the few Americans ever to cross the 50-mile line the Air Force used to define the edge of space. Investigators would spend months untangling what actually happened between the moment the aircraft left its mothership and the moment it broke apart in the sky over Randsburg, California. The X-15 was a joint project of NASA, the Air Force and the Navy, built by North American Aviation to explore what happened to an aircraft and a pilot at the boundary between atmosphere and space. 3 of them were built. They flew faster and higher than anything with wings had flown before, dropped from beneath the wing of a modified B-52, and boosted by a rocket engine that burned for less than 90 seconds. Every flight carried risk that had no precedent, because nobody had done this before and there was no manual for it. Adams had joined the program in July 1966, its 12th and final pilot, after realizing the Air Force Space Station project he'd trained for was unlikely to fly. He had already survived a ruptured fuel tank, a lost cabin pressure, an engine that failed to ignite twice. On his 3rd flight, he had reported vertigo during the climb. That detail would matter later. Flight 191, officially designated 36597, dropped away from the B-52 named Balls 8 at around 10:30 in the morning, released over Delamar Dry Lake in Nevada at 45,000 feet. Adams' wife and mother were watching from the NASA control room at Edwards Air Force Base. The mission carried 7 separate experiments packed into the nose and fuselage: an ultraviolet study of the rocket's own exhaust plume, solar spectrum measurements, a micrometeorite collector, a test of ablative heat shield material intended for the Saturn rocket program. The flight plan called for a climb past 250,000 feet and a top speed above Mach 5. Adams reached 266,000 feet, more than 50 miles up, enough to qualify him for astronaut wings under Air Force rules. He would receive them posthumously. The trouble began during the climb, before the aircraft had even reached its peak altitude. One of the onboard experiments used a commercial electronic component that had not been properly qualified for the X-15's environment. It generated an electrical disturbance that rippled through the flight control system, producing a brief, unwanted motion in 3 of the servo actuators that steered the aircraft. The disturbance tripped the dampers in the plane's adaptive control system, the electronics that kept the X-15 stable at speeds and altitudes where conventional aerodynamic surfaces barely worked. Adams reset the dampers and continued the climb. It looked, at that point, like a manageable glitch. It was the first domino. To gather data for one of the onboard experiments, Adams switched a cockpit display from its normal setting, which showed yaw angle, into a vernier attitude mode that gave him finer readings for the instrument he needed. The plan was simple: use the alternate display briefly, then switch it back before the descent and landing approach. It was a routine procedure he had used before, but it meant that for a critical stretch of the flight, the instrument that would have told him his nose was swinging off course was quietly displaying something else. He was flying blind to the one number that mattered most, and he had no way of knowing it. Near the top of the climb, Adams began a planned wing-rocking maneuver, a gentle side-to-side roll meant to let an onboard camera scan the horizon for a separate experiment. Ground control, watching his telemetry from Dryden Flight Research Center, noticed the rocking was more aggressive than planned, 2 to 3 times the intended amplitude. Nobody flagged it as dangerous. Pilots dealt with minor control quirks on nearly every X-15 flight. It was, in a strange way, the normal condition of pushing an experimental aircraft this hard. When Adams finished the maneuver, the nose of the X-15 began a slow, almost lazy drift away from its intended heading. 40 seconds later, as the aircraft reached its peak altitude of 266,000 feet, it was 15 degrees off course. For a moment, the drift paused. The X-15 hung there, at the top of its arc, pointed in the wrong direction, and nobody in the cockpit or on the ground fully registered it. Then the drift resumed. Within 30 seconds, the aircraft's flight path and its physical orientation were no longer aligned at all. Adams was now descending sideways, at close to a right angle to the direction he was actually traveling. On the radio, his voice carried a note ground controllers hadn't heard from him before. He said the aircraft felt squirrely. Pete Knight, a fellow X-15 pilot serving as mission controller that day, told him he was a little high but in good shape, still reading normal parameters on the instruments available in the control room. Nobody in that room had a display showing Adams' actual heading. That gap in the ground's own instrumentation would turn out to be as consequential as anything happening in the cockpit. The X-15 kept descending sideways into thickening air. At 230,000 feet, still moving at roughly Mach 5, the mismatch between its direction of travel and its physical attitude became more than the aircraft's stability could absorb. It entered a spin. No pilot had ever put an X-15 into a spin at hypersonic speed, and no one on the ground had a procedure to offer him because no one had ever needed one. Adams got on the radio and said the words directly, "I'm in a spin." There was nothing anyone at Dryden could tell him. The aircraft was writing its own emergency procedure in real time, 6 figures above the Mojave, with a pilot who had never trained for this specific failure because it had never happened before. What Adams did next likely saved nothing, but it wasn't for lack of trying. He held the controls against the spin, working both the conventional aerodynamic surfaces and the reaction control jets mounted in the nose and wingtips, the same thrusters used for attitude control above the atmosphere. Through some combination of his inputs and the aircraft's own inherent stability, the X-15 came out of the spin at around 118,000 feet. It should have been the turning point of the story. Instead, Adams found himself in a new and different emergency, an inverted dive, nose down at an angle between 40 and 45 degrees, speed climbing back toward Mach 4.7. The aircraft's flight control system, already strained by everything that had come before, began to saturate. A self-sustaining pitch oscillation set in, the nose porpoising up and down in a cycle the system couldn't damp out, feeding on itself as the X-15 plunged into denser and denser air. It was losing altitude at a rate approaching 160,000 feet per minute. Whatever margin existed to sort this out was shrinking by the second, and the aircraft was heading toward a part of the atmosphere where aerodynamic loads would start to matter in a way they hadn't at the edge of space. By 65,000 feet, the X-15 was diving at Mach 3.93. Dynamic pressure was climbing by nearly 100 pounds per square foot every second. The G-forces on the airframe exceeded 15 vertically and 8 laterally, both well past what the vehicle had been built to withstand. Something had to give, and it gave at 62,000 feet. The wings and tail surfaces separated from the fuselage. The aircraft that had carried Adams to the edge of space 9 minutes earlier came apart into several large pieces, still traveling close to 4,000 miles an hour, and fell toward the desert floor north of the small town of Randsburg, California. Adams did not eject. Whether he attempted to, or whether the forces in those final seconds made it impossible, investigators could never determine with certainty. His body was found in the forward section of the fuselage, which crashed near what would later become his memorial site. Most of the wreckage scattered across private and public land in the area. A search team recovered the cockpit camera days after the crash, but the film cartridge that would have shown exactly what Adams saw in his final minute was missing. Engineers eventually theorized it had separated from the heavier camera housing and drifted further on the winds at altitude. It turned up 2 weeks later, found by a search organized by a Flight Research Center engineer. What was on it added detail, but it didn't change the fundamental outline investigators had already pieced together from telemetry and instrument recordings. The accident board's conclusions were careful, and in some ways more unsettling than a single clean mechanical failure would have been. The cockpit instrumentation, they found, had actually been functioning correctly for most of the flight. Adams lost control not because a gauge lied to him, but because of a combination of factors stacking on top of each other. The distraction created by the earlier electrical disturbance, a display switched to the wrong mode at the wrong moment, and quite possibly a return of the vertigo he had reported on an earlier flight. He had been managing several problems at once, none of them individually catastrophic, and the combination had been enough. Investigators also noted that ground control's own displays hadn't shown Adams' actual heading at any point during the mission, which meant that even a fully alert team on the ground had no way of catching the drift before it became unrecoverable. The board's recommendations were specific and were adopted. Dryden's control room would be fitted with a telemetered heading indicator so that future controllers could see what a pilot's instruments were actually reporting instead of a narrower set of proxy readings. X-15 pilot candidates would be medically screened for sensitivity in the inner ear, the vertigo risk that had already touched 2 of Adam's flights before it may have touched his last one. Neither change could undo what had happened over Randsburg, but both addressed the exact gaps that had let a 15-degree drift go unnoticed until it was a spin. The program itself did not survive much longer. The X-15 continued flying for less than a year after Adam's death, and by the end of 1968 the project was shut down, a decision driven mainly by budget pressure and the fact that its research goals had largely been met, but arriving in the shadow of the one fatality the program had spent a decade trying to avoid. Adams was posthumously awarded Air Force astronaut wings for the flight that killed him, one of the small number of X-15 pilots to qualify. His name sits less prominently in public memory than the Mercury or Apollo astronauts who flew after him, even though the data his program generated shaped how NASA understood high-speed flight control years before anyone strapped into a space shuttle. What changed, in the end, wasn't the aircraft. It was the assumption that a pilot's instruments and a ground controller's instruments were telling the same story. They weren't, and for 40 seconds in November 1967, that gap was the only thing standing between a routine research flight and the one death the X-15 program ever recorded. If you want more of these deep dives into the moments that quietly rewrote how we fly and fly into space, subscribe, and let me know in the comments which forgotten test flight you think deserves the same treatment next.